Hello, I'm Trevor Brown, the Chief Revenue Officer at DCN Diagnostics, and this is Expert Insights Podcast. Today, I'm joined by our Chief Operating Officer, Pat Vaughan, who runs operations across DCN's contract assay development, engineering, and manufacturing service businesses. Pat recently wrote a piece called Bridging Assay Development, Manufacturing for Lateral Flow Success, and it actually addresses one of the biggest pitfalls of rapid assay development programs. Pat, this is my first time hosting Expert Insights, and I'm excited for us to sit down and talk about this topic, which is near and dear to my heart, and I certainly know yours as well.
Thank you, Trevor. Yeah, no, I'm looking forward to this. You know, this is a conversation that comes up a lot at DCN with our clients and prospective clients. So yeah, exciting stuff.
Excellent. Thank you. Yeah, the handoff between development and manufacturing is something I've seen over and over again in my career in diagnostics. Generally speaking, where the most friction occurs, because both parties are working earnestly in trying to make this work. And I think getting some insights from your side of how this is going to translate from a lateral flow perspective would be very helpful for our audience. You make a claim early in the article that I think catches people a bit off guard. You say that most lateral flow programs that fail don't fail in the development phase. If they do, it's part of the process. Where that failure hurts is when that high-performing assay working on the bench starts to lose that performance when it comes to scaling up the manufacturing. So what does that failure actually look like in practice?
The physical failure can look like many things. And, many scientists and manufacturers out there will recognize, it could be suddenly you get non-specific binding that appears and the R&D people are saying, well, we never saw that, but the manufacturing people are saying, yeah, well, we see that. Or suddenly you start to see a signal drift across the whole production run. The early strips are good, late strips are bad, or vice versa, right? So, what used to work passed all the time in R&D, suddenly now you're seeing differences. It could be something like the material is breaking on the reel-to-reel, on the scaled up automated equipment, and the scientists say, well, we never saw that in the lab. So, it can be a lot of physical things, but a lot of the time, what's the pain point is the failure can be intermittent. So it could be an irreproducible result on the manufacturing line. So, the scientists are called back in, but they can't reproduce it. And they're kind of scratching their head as to what's this, because it's not, you can't just summon it by demand, basically. So it's kind of like there's a lot of probing around. Obviously, the R&D scientists are going to start chasing the chemistry, right? That's just their first point of call. It could be something very physical on the manufacturing line as well. That's where the conflicts and the issues occur, basically.
Yeah, I like to describe it. It's where the fist fights happen between R&D and manufacturing.
Right.
So in the article, you describe a paradox. So a lot of these assays that are performing beautifully at the bench, great performance characteristics, can be quite challenging to actual manufacture, even with a well-designed manufacturing line. And that can be introducing anomalies that can be hard to troubleshoot. And then you get this back and forth, he said, she said, between the manufacturing and assay development groups. How does something like this that works that well on the bench end up being the problem?
Great question. I think you look at that from both directions, both from R&D and from manufacturing. So a great R&D performance does not equal a manufacturable product. Okay. And then look at it the other way, is that a high throughput manufacturing does not equal a robust assay performance, right? They're two very linked events, but they are two separate questions as well. So think about it from the point of view of the bench scientist, the R&D scientist. That's a very different, maybe even a controlled environment. It's forgiving because you have an expert scientist working on this assay. Usually it's small pieces of material. They're lying flat on your development equipment. There's no real mechanical stress on it. They can take their time. The speed is slow. There's no pressure of production there. And the assay works under these conditions. But the assay works. It's not necessarily the product at that stage. So what the R&D person is looking at is really a prototype or a concept. It's not necessarily a product at that stage. Manufacturing is when somebody comes along and say, okay, I need it to be robust, reproducible. They're looking at it on a much larger scale. It could take all day to do something because there's so much of it to be done. And then obviously the manufacturing think about manufacturing. They need to make this over many months or years. So they're going to get so many different lots of nitrocellulose, lots of pads, lots of antibodies and stuff that may all be just slightly different all within the vendor specification, but all subtle differences that will cause issues potentially. Manufacturing is now introducing variation. Okay, and this can go on for many years. That's by nature, you should expect that, but unfortunately, that's not what happens. So suddenly you take something that's working really well, put it onto the manufacturing line. It's now going to run faster because you want to reduce the labor associated with it. So you need to get it through material, maybe going through drying towers and not ovens, basically. So the original assay is doing what it was asked to do, but it wasn't designed for, almost like a different set of physics, basically, right? So that's where the issues arise and where the two sides, don't meet head on and have a nice handshake.
So you're careful to say this is rarely any one team's fault. It really comes from treating development and manufacturing as really sequential steps rather than one integrated activity. What do you think manufacturing or development teams still make this mistake?
I suppose most organizations are set up that way, where you have a R&D team and a separate manufacturing department or a manufacturing team. They could be in separate buildings. Sometimes they could be in separate companies, right? If both aspects are outsourced. So that kind of structure, it really promotes that sequential thinking rather than a combined thinking. In the CDMO business, where your development partner and your manufacturing partner are different companies, maybe you have communication silos. There's different incentives for both parties as well. So they're not necessarily playing off the same financial hymn sheet as well. So, think about it, the milestones for each. For a development milestone, they reward lab performance, how sensitive your assay is, how specific it is, the limit of detection. Nobody in R&D is going to get any tap on the back or credit for, my assay, it tolerates, variable line speed variation in manufacturing, right? So, or performs consistently across multiple shifts. R&D scientists don't think about that, but that's the reality for manufacturing. And then, when teams come to pick a contract manufacturer, the development is already done. So by the time manufacturing gets involved, the design is locked. So that obviously can be a real issue. So really you need to kind of consider that design for manufacturing. And, it's really misunderstood. People think of design for manufacturing as like tech transfer, right? And it's like you check it off your checklist when you get to that portion. And really it's not, right? It's not tech transfer. It's actually, it should be part of the design of the product. It's as important as selecting the right antibody, okay, as to what are your manufacturing parameters. And they're important inputs for the R&D scientist, okay, not just for the manufacturing personnel.
Do you see this happening more with early stage companies, assays that have maybe been spun out of academic institutions and where maybe there's not that depth of experience in bringing a product to market necessarily at the start?
Absolutely. That's a prime example of where you're going to see this sort of thing, because really, again, those people are being credited, you've developed an assay. Well, you've developed the proof of concept, or maybe, and let's call it an assay, right? But it's not a product. And an assay and a product can be two completely different things. A product is where you take the assay and can manufacture it. An assay doesn't mean that you can manufacture it. So, and that specifically, yes, I mean, for a startup company, they are all focused on getting the assay to work. It's like manufacturing that, well, that's somebody else's issue down the line, and we'll cross that bridge when we come to it. Well, unfortunately, when you get to that bridge, it could be too late, or maybe not too late, but it's going to be an expensive walk across that bridge, basically.
I mean, yeah, you say a lot that assay design decisions in that development phase really embed a manufacturing consequence. And I think that bears true in what you've just said. Do you have one example where R&D teams kind of underestimate this? In the article, you referenced sort of a conjugate behavior, for example, doing long dispensing runs, and choice of that while in development might not factor in the time and processing in a manufacturing scale.
Yep. Yeah, absolutely. So let's take, leaving aside, let's say you can make the conjugate okay in a small volume or a large volume, right? But moving on from there as to how you use it, conjugates are typically nanoparticles, so they're suspended solids, okay? So you shake up the tube, you can see everything swirling around and everything is great. But when the bench scientist is making a small little batch, okay, they have a little tube of it, they're dispensing it, they may a little swirl it, even, they're potentially holding it in their hand, or it's just on the desk in front of them. Everything is kind of controlled, right? So now on a production run could be running all day, and you have multiple rolls of material that need to be sprayed with the conjugate. The conjugate is sitting on your dispenser, okay? It's solid. It doesn't always have to, but it could actually start to settle. So now if you imagine it's settling, so the bottom of that tube is going to be more concentrated. So what you find then is early on in the material that you spray early in the day is getting one concentration of those particles. The stuff that's later in the day is getting a lot more concentrated solution, way more particles. So when you go to transform that into strips for testing, it's going to be totally different. You may get, big whopping results and big strong positives later in the day versus earlier in the day. So ultimately you could actually start generating, false positives basically, or non-specific findings. So it's very, very difficult. That's just one example of conjugate, but the other thing follows for all materials, whether it's membranes, antibodies and stuff as well, is that you get lot to lot variation. So it's the same membrane maybe, but a different lot from the manufacturer. You need to make sure you're including that in your development. You can't leave your manufacturing colleagues to figure that one out later.
Thinking about this is a great example. Maybe you could start by giving a little bit of an explanation of kind of what lateral flow manufacturing kind of actually looks like. And then, the detail I want you to walk through is the concept that, there's some of these first strips that you run may not perform nearly the same as the last strips on the line. But maybe to set the stage, kind of what happens in an actual lateral flow manufacturing scenario.
Okay, so I'm walking into the lab. I've got a full agenda for the day. I'm going to start, and maybe over, and it's actually for manufacturing, it's going to be over several days. So you're making all your buffer solutions, you're making your striping solutions, you're doing your conjugations, and you're getting everything ready now for dispensing. And really, it's dispensing is the key, unique part of manufacturing. So in the lab, the scientist maybe striped a few feet or a few meters of material. In manufacturing, you're setting up to maybe potentially dispense on rolls of material, maybe a 100-meter roll. Maybe the manufacturing run is 2 or 3 or 9 rolls of material. So you're going to start spraying or striping. But remember, all through that time, your reagents are sitting out live, potentially at room temperature, and then you're going to stripe one roll, you have to undo everything, put on the next roll of material, and it's a continuous process throughout the entire day, okay? So that's what it's going to be very different. The scientist doing a few quick experiments just looked at a small portion of material and maybe did the striping and spraying or whatever it is in an hour. The manufacturing technician is looking at this in an all-day event, or maybe even over multiple days. Okay, so if I go back to my example now of the conjugate sitting there all day and it's settling out, maybe I need to consider, okay, well, to avoid it settling, I'm going to start mixing it or recirculating it in some way. Great idea. Now I've solved the technical problem of this, difference between early morning and late afternoon because the concentration is identical. Well, what you need to consider then is that's a late in the game decision to make, right? Because, well, what's that vortexing or recirculation going to do? Is that going to destroy the conjugate in some way? Is it a lot of shearing forces? It's going to create, maybe introduce a lot of air bubbles into it. You're going to start foaming. Trevor, you and I have probably spent many years in the lab and where you're shaking a little tube and suddenly you get that little froth or foam on the top. Well, we were all taught that that's not good because what that includes is denatured protein there. So now suddenly you've lost most of your antibody, okay? So what seemed like a great idea to start mixing the stuff, now you're ruining your conjugate. So the moral of the story that is let the R&D scientist with a manufacturing brain on their head figure that one out during development. So it's a no-brainer once it gets to manufacturing. It's okay because everybody knew from the start that this solution will sit on that machine all day long and needs to be, 100% performance level, 9 a.m. in the morning, 4 or 5 p.m. in the afternoon, and it needs to act the same. So those issues should be found and solved in development and not in manufacturing.
You touched on materials too, and the difference between going on the bench and in in manufacturing, which is reel to reel, where hundreds of meters of media are placed in a reel format, like a film reel, and strung through a machine to be deposited and striped. So what role do materials actually play in all of this as well, in terms of variability in the scale up for manufacturing? You mentioned in the article that nitrocellulose can vary between lots, within that lot, beginning and end of the lot. Membrane and pad interactions can only show up under continuous processing, not sort of bench type processing. What are ways that assays can end up optimized for conditions that don't really exist on the manufacturing line?
Yeah, for sure. And let me say, before I start going into talking about all the variability in these materials, the materials we use today compared to what we used 20, 30 years ago are, today they're incredible, okay? In the early days of lateral flow, we all use material that really wasn't designed for lateral flow. It was probably designed for something not even within the life sciences. Okay, so you kind of figured out, oh, this might work here. Today they are very refined, and the manufacturers do an incredible job in trying to get as much consistency. But these materials are made in large volumes. Okay, so like nitrocellulose, we kind of colloquially say that it covers the entire football pitch, and then you start cutting it up into rolls after that. So how do you ensure that uniformity is across the entire football pitch, where you're only getting a little portion of it? So from roll to roll and from batch to batch, you get subtle differences. They're all within the specification that the vendor specifies. That's fine. That's not a problem. But those subtle differences, if your assay is very touchy or very sensitive to some small variances, you're going to find that. What we're saying is it's the development scientists should be finding that, understanding that, and building those tolerances into the product design. You can't wait until your manufacturing colleagues are figuring that out, because 6 months into manufacturing, suddenly they get a new lot of material and it acts completely different. It's within the specification that the vendor says, but now it's impacting your assay. So that's part of the transformation from an assay to a product. Part of that is ensuring that every time you go to make it, you can make it, even though you have a different lot of antibody, a different lot of membrane, and so forth. And then the processing of that as well could be different. So think about it when you're striping just a small piece of membrane and then you're laminating it onto your card. Everything is flat on the bench in front of you. When you're going to reel for high throughput automation, everything is on a roll. It's curved. Now everything has a curvature. Is that going to impact your assay? And also, is it going to impact the tension on the materials as they're laminated as well? Is it going to stretch some of the material, or is it going to compress some of the material? All of those could be very influential and impacting the performance of your assay. So there's a lot of things to go on. But the moral of the story is, look, find, and fix these things in development, not in manufacturing.
That makes sense. And I think we're transitioning nicely into an area that is sort of the macroscopically, thinking about the physics of doing anything at scale. And we understand how lateral flow, applies to almost any diagnostic. I certainly have a lot of experience, some of it negative, where assays have just fallen apart at the manufacturing scale. Just wasn't designed up front to handle it, and with very dire consequences. When I talk to people who are not that familiar with how diagnostics are developed, I use an analogy that cupcakes, baking. You might be able to bake a dozen cupcakes and everybody loves them, right? But if you're asked to make 1,000 cupcakes using the same recipe that you just scale up by multiplying the ingredients, you're absolutely not going to get the same taste or texture. It's just not going to work the same. And in reel-to-reel, it's a different environment, not just a faster version of the bench. So for someone who's only really working on benchtop or batch platforms, what kind of differences come into play as you start to move into higher scale, what you've touched upon already?
Like really on the reel-to-reel automation, because you need that for high throughput to drive your unit costs down. You need to scale to that level and to keep up with hopefully with your market demand as well. So on the reel-to-reel, well, the first main difference is your material is moving. On the bench level, where the scientist did it, everything is fully supported. It's lying flat. On the reel-to-reel, now that material is being dragged from the outlet reel to the uptake reel, and it's moving all the time. So Everything is variable there. So, and there's tension involved. So wet materials can now suddenly behave differently. So you picked up a roll of dry material, it looks fine. You run that from a roll to a roll and it seems okay. But now you could be dipping it or spraying it. It gets wet. What's that doing to, let's say, the tensile strength of it? And it could snap, right? So the manufacturer is looking at that and saying, what the heck has gone on? That's where the scientists should have figured that out already. So that material was great when it was lying on the bench, but now when it's on a roll and it's getting wet, it's lost its tensile strength. So that's a very important, and that's a very specific example, but it's a very important thing to think about during development. And then as it's going through on the reel-to-reel, you have to dry it. Now it's going to dry in a drying tower at a certain temperature. Because it's moving, it's only going to be in that drying tower for a few minutes. Whereas the bench scientist, when they had striped or sprayed it, they just stuck into the oven and walked away. They said, well, it was dry. There, now you're looking at the difference between two drying processes as well. An oven, where you can have almost unlimited time, and a drying tower, which you have very limited time. Those two things are very, very different. And there could be pros and cons of either one, but you need to design that into the product, because are you over drying something? Are you under drying something? You know, somebody as simple as using the oven, how do you know it was at that temperature for the 30 minutes or the hour? When you turned your back and walked away, your colleagues were there pulling their materials in and out, and the door of the oven might have been open, right? So how do you know that was at a constant temperature for that amount of time? So all of those things need to be taken into account. And that's where part of development should have been putting that assay on the reel-to-reel and figuring out all those nuances and designing the system so that the reel-to-reel and the drying tower process is working, basically. So that, and then, you know, there's a whole thing about what's touching the material. All of those things vary as well. The speed, the vibration, all of those things can cause things to move. One line can run into another. You need to take all of that into account.
That's great. I think many of our listeners, they're really competent assay developers. They're capable of developing accurate, specific assays at the lab scale. Many have actually come to our basic lateral flow training course. Our next one runs in September, so I'm putting a plug in for anyone who may be interested in that. For a team that manufactures in-house and thinks it has all of this covered, you know, what does the development to manufacturing gap still bite them, and how should they think about this design for manufacturing concept?
Again, kind of following on from what I was just saying about moving from bench to reel, there's a lot of different subtle, maybe some of them are not so subtle differences. So if I'm spraying something at the bench level, it's lying on a flat platform, I'm spraying, basically material is sitting in that solution. When I'm spraying something on the reel, I could spray it so hard that it can actually go right through that material. So that could be a fact of life. I may need to turn down the PSI on those air jets or whatever, but I may also need to figure out, I need to spray more material onto the reel-to-reel material so that there's enough left to make sure that the assay performance is correct at the end of the production run. So there's a lot of nuances there that you have to. That's part of the design, okay? Is just because you were able to spray it on an XYZ platform, for instance, doesn't mean that you use the exact same parameters. And the same goes for dipping or whatever else you're doing, really. You need to be conscious of those differences and take them into account.
When we think about manufacturing and designing for manufacturer from the bench to the manufacturing, you have this hard line between an assay that can work and an assay that can be made. You kind of call it this hero batch or golden batch. You say these conditions rarely survive automation. In many cases, you may be proud about what the performance is until it gets to that automation. What's the type of question that a team should be asking instead of, does it work on the development side? What are the other questions they should be asking?
I guess that's the classical conundrum that a lot of people kind of encounter. So the hero batch, or, you know, we call it the golden batch. That's the word I used to use in my past as well. But I know it's referred to as
magic hands.
Yes, exactly. Or green thumbs. So, you know, what that golden batch or hero batch proves is that, yes, the chemistry is possible. But for me, that's a prototype, or maybe it's even just a concept, okay? It doesn't prove that the assay is manufacturable. Therefore, it's not a product yet, okay? So the golden batch is a prototype. You know, it's always the early output. You should have an early prototype to say, okay, well, I think I've selected the right antibodies and so forth. I think I can hit roughly where it needs to be in sensitivity and specificity. I'm kind of good to go on to the next step. You're not ready for manufacturing. Okay, so you basically design and build it to be repeatable. You're not designing it just to impress somebody, okay, with saying, I have this sensitivity. Well, sensitivity of a prototype or a concept, that's not going to make you any money on the marketplace. It'll never even get to it. So it's more, you should be asking yourself, can somebody on the manufacturing floor make this over multiple shifts during the day, into the night maybe, and then with a whole load of different batches coming through, incoming, because the vendor has finished one lot and is going to send you another lot. Is it going to work then? And you have to remember how the assay was designed, right? If it was designed where all the specifications were 10 out of 10, you had all the dials turned up high, well, you've left the manufacturing guys nothing to turn, right? Because if they turn it down, they're just going to lose performance. You have to design it where it's kind of in the middle, where you can crank it up or down to basically incorporate or tolerate all those variances, basically, right? It's kind of like, so it needs to be designed to be built at scale. It's kind of like, golfers, I remember the saying, you drive for show and you put for dough, right? So it's the same thing with a product. You need all that performance like sensitivity and specificity and LOD, but you need to be able to make it at scale. That's what the product is. The prototype or concept is not the product.
Interesting. Yeah. And I think you mentioned that if an assay is only working with someone with golden hands or an expert, many lateral flows are designed to be used by regular general population. If it's only working on the bench with someone who does this day in and day out, how do you kind of deliver that message to people who are really confident in the bench data, but it's not been robustly tested, it's not gone through manufacturing for that, guard banding? And how do you deliver this message without telling them that what they're doing is not completely wrong?
Yeah, without hurting feelings, basically, or getting somebody bent out of shape, right? So the R&D scientists, their bench data, it's real, right? It's good. It shows that the chemistry is working. But again, you're at a certain stage in your development. You're not finished. You're at a prototype level. And you have an assay, okay? So it says, okay, the assay works. That doesn't mean that the process to produce that assay at high throughput is robust enough so that you actually have a product. There are two different things. The bench scientist has proven something really important, but the second part of their job is let's prove that it's manufacturable, which is an additional but an imperative objective of development. That's not the objective of manufacturing. They should be following instructions and the correct product should pop out the other end, right? That's the job of the developer. So you need to determine that what you're doing, yes, sure, the chemistry works, but the process works as well to make sure that you can produce the product. Because think about it, you have to say, this assay or prototype will now have to be made and work with huge differences in conditions. Will it still pass and come out the other end? So you really have to kind of think about it and take it through the whole process and make sure it works, yes, at small scale and then at a high scale. The goal here is not to invalidate what the scientists did. It's to extend that proof basically into proving manufacturability. And both are necessary to ship that product.
Let's shift a little bit to some of the impacts of these kind of decisions within development and manufacturing and when things go wrong, right? There's costs involved here. Yield loss on the development line, right? Could be days, few weeks of small amounts of the project, right? But they could be the entire margin of the product, when built at scale, and you have to rework an entire batch, right, for the lateral flow line. So, talk a bit about why first pass success is so important. It's so much more unforgiving.
Yeah. So they're the kind of messages you get from your CFO, right? So you think everything is rosy. You've got great numbers of sensitivity and specificity. And suddenly that email says, well, why is it costing us so much to make this, right? So I'm sure that's daunting for a lot of people. So you really need to do the math early in the process. So you need to model that production yield. So are you getting 100% yield? You'll never have that, right? So are you getting 95%, 90%, 85%? All may be viable, but all may not be as well. So 95% saying, okay, that's viable, but dropping to 90%, it's not economically viable. So you really have to determine that loss is that it could be totally insignificant in during development, right? So if I produce 50 strips and 45 work, fine, it's not a big deal. But if I'm making 100,000 strips and 5,000 don't work, that's a big deal, right? So there's a very big difference. So you need to look at that early. There's lots of different reasons for that as well. As using the higher throughput equipment, there's a lot of dead volume loss of maybe very expensive reagents. And this is not just for lateral flow. In the pumps, you have to load up expensive conjugate or antibody. It's the same for making an ELISA. Let's say you have an Oyster Bay or something like that. All those pumps and lines contain dead volume that'll never see the product because they're just there. You need to load so much more and they'll all go in the trash. In R&D, you were able to kind of figure all that out. And, just when you're doing everything so manually, that's not an issue. But that could be large economic impact on or financial impact on your product. So, and things like, when you're running a roll of material from one roll to the next, if you have to set it up before you start spraying, you're losing the first part of the roll. So you need to consider using leader sequences and stuff as well. So you're actually spraying 100% of the material and not just using the beginning and the end of the roll just as roll up material, kind of thing like that. So all of those impact what's happening and the economics of it. Those need to be considered during development, not when it gets to manufacturing.
So it brings up a great point because we speak with a lot of customers who have assays or contemplating assay development opportunities. Not every assay developer manufactures. And so if you're not actually concerned about the manufacturing phase, how are you going to validate or design for manufacture, right? Our mantra here at DCN, design for manufacture from the very beginning. And because we do both development and manufacturing, we're able to manage and optimize those conditions. So what does that look like in practice from a company like DCN compared to how maybe other teams might run a program where they're development first and then seeking an outsourced manufacturer?
Here at DCN, obviously the assay development scientists and the manufacturing engineers are all in the same room all day, every day, basically. And they're, for a program, they're together from day one. It's not a handoff. It's, I suppose you'd call it a co-design, right? So the manufacturing engineer is asking, well, what does the reel-to-reel going to do to this? While the assay scientist is still choosing the chemistry, right? Or the materials. They're saying, oh, this pad works great. But the manufacturing technician is saying, yeah, that's great. But when that gets wet, that's not going to stay on the rollers, basically. It's going to break, kind of thing like that. So it's a hand-in-hand development. Manufacturing isn't an afterthought. It's an early input. And the other way we do it here at DCN as well is that all our development scientists are highly trained in manufacturing as well. They are developing the product thinking as a manufacturer, right? Because they've all worked in manufacturing as well. We interchange people a lot. They're hands-on on all aspects of it because we want them to learn, know, and understand all aspects of product development. And product development isn't just the chemistry of selecting the antibodies. It's making sure that we can package it into like tens of thousands of devices into kits and it's going out the door. Every time we go to manufacture something, it works and we can ship it. So they're working hand in hand from day one. So you're really, it's like one of your inputs is not, oh, I need an LOD or sensitivity of X. It should be, what's the manufacturable performance? What do I need to do to release this to the market? That's an input. So now work back from there, and that's how I start to design my product. So it's not an afterthought or, it's not a nice to have saying, oh, well, the results I have are great for a scientific publication, or these are going to look great in our FDA submission. That's not going to make it a manufacturable product. So those design inputs, manufacturing inputs are so important as part of that. So I would say process development is an integral part of assay development. You can't distinguish them. They are interlocked, intertwined, and you should be looking at both. Unless if your business is, I just want to see if a prototype works. that's fine, but that's not product development. Product development really is your assay and your process working cohesively together. So that design for manufacturing, it's a misnomer, because people think of it, as I said earlier, as they think about it as, oh, that's tech transfer. No, design for manufacturing happens from day one. And it's those manufacturing constraints are inputted into your design inputs from day one.
What happens then, if someone has an assay that they've developed and want us to manufacture it? Where do you see the biggest problems, or where have you seen some of the biggest issues that with a fully baked assay and wants us to scale it up for them? How often does that just go off without a hitch?
It doesn't go off without a hitch very often. There's always issues. I mean, yeah, sure. We get some people that even have a concept and they're saying, can you manufacture this? And we're saying, wow, you missed a step, right? But let's say they have designed it. That happens a lot, again, because, as we've been talking here, is that just because the assay strips or the prototypes are hitting sensitivity or limit of detection, it doesn't mean it's manufacturable. So for all the reasons we've been laying out today, that's what comes up. So that conversation, it can be very awkward, because this customer comes in, they're saying, we're ready for manufacturing because our development scientists have said it's ready. It looks great. It's got great CVs. It's got great sensitivity. But, again, could that scientist go back and make a nice small batch of it and it'll work exactly the same again? Of course. Now, they need to consider if they have to use a different lot of membrane or antibody in the meantime. But let's say they use the same one, that'll pop out. But that's not manufacturing. So it is a real important question, and that we're the ones ending up having to answer it. And unfortunately, as you know, Trevor, it's a tough pill to swallow, right? Because it usually means, suddenly you had a financial projection of where your product was going to be hitting the market. And suddenly now you're going to have to say, well, now I have to finance basically almost a redevelopment. And really it is redevelopment. It's not doing something for the sake of doing it. It's because it hasn't been designed for manufacturing. So
there can be a costly mistake sometimes coming to assume that the next step is manufacturing.
Yeah.
So you close the article with a 5-step framework on how this approach should be taken. Which one have you seen repeatedly move the needle the most, for folks as they consider their development programs?
Involve manufacturing from day one. It's part of assay design. Or make sure that your development is being run by, scientists that are fluent in manufacturing. Okay. Define the manufacturing performance. That's an important input before going off and trying to optimize an assay, right? Think about the scaled process. You scale it during optimization and development, not afterwards. You stress it, do your guard band studies, you stress it to almost try and break it so that the scientist can have it fixed by the time it gets to manufacturing. And then you're optimizing for the total system, right? It's not just the chemistry, it's not just running on a reel-to-reel, it's the entire system. And you're not looking at any one metric like sensitivity. It means, is there a viable product that meets all the specifications popping out at the other end? So to answer your question, overarching, it's designed for manufacturing. But maybe what's a critical step is, I would say, is getting into that scaled up process and equipment during development, because that is part of assay development. So early automation means that you'll have the truth about your assay, right? Does it work or not when I go to manufacture it? And that's the most inexpensive time to deal with those issues, right? Where it's part of development. You're not finding out the failure mode when you have a production line stalled and there's no product coming out the other.
You've locked things down otherwise.
Yes, yeah. Exactly. Yeah.
Well, I really appreciate getting the insights from the ground at kind of what it takes to consider the scale-up process from development. If there's one thing a listener would take away from today's discussion, what would you want it to be?
Maybe I'm sounding like a broken record, but it's designed for manufacturing, and either get your manufacturing people involved from day one or use development people that are fluent in manufacturing. Because remember, they're both coming at it from the different directions. When they're not working together, if they're siloed, their performance is assessed very differently, right? The scientist is saying, well, how sensitive can you make the assay? The manufacturer is being asked, can you produce this at the lowest possible cost, most reproducible, and it's high performance? Two very different things. And sometimes that actually comes from day one, from when you're going out raising funds from your investor. The investor hears, it's sensitive, it can pick something up. sometimes they're not interested in saying, well, it'll work with all the variations of manufacturing. That's not going to get or have any interest at a board meeting, right? It's more the economics of it. I'm giving you money to develop a product. I need to hear that it can detect whatever antigen you're looking at, rather than I can make, 50,000 of these, because maybe in their mind, that's a way down the line as well. But in reality, it's not, right? So I would say is for everybody, for the startup, for the investor, for the manufacturing people, for the R&D people, it's a combined approach from day one, basically.
I think the two things that investors are going to care about, and having some experience here, how much is it going to cost and when can you start selling it? And if you're not designing for manufacturing, it sounds like it could cost a lot and the time could be pretty expensive, a lot more than if you started right from the right go.
Yeah.
So
the later the time, that's the more expensive time, basically, right?
Yeah. Well, this has been great, Pat. I want to thank you so much for walking us through what is maybe not so understood in the development process. I think, assay development is approachable. We have a lot of expert and great scientists, but there's a particular set of processes that need to be undertaken to get to develop something for manufacturing, which is the goal of most of our customers. They all come to us with a goal in mind, and that is commercial success of the assay that they're building. And that commercial success is usually tens of thousands of units built, at a time to get to market. For listeners who want the full argument on which this podcast was based, feel free to go back and see Pat's article, Bridging Assay Development and Manufacturing for Lateral Flow Success, which is on dcndx.com. And Pat, I want to thank you again. And until next time.
Thank you, Trevor. It's been a pleasure. And, we can make it work, right? It's never too late. It may be a little expensive when it's late, but, if anybody has kind of gone down the road and saying, oh, no, we didn't follow what he's just saying there, well, give us a call and we can figure it out for you.
Sounds great. All right. Thanks. Till next time.
All righty. Thank you, Trevor. Bye-bye.